Okay, so as Bill said, I'm going to be talking about Profvis and profiling tools for faster R code. So thanks everybody for coming. I just want to say that. So here's a question that probably comes up a lot if you work with R a lot, which is how do I make my R code faster? And that naturally leads to another question, which is why is my R code slow? And my strategy for this talk is I'm going to walk you through a couple examples and show you some of the tools, that can help you diagnose these problems and speed up your code. And hopefully we'll also learn a bit about a few particular things in R that might be slow and surprisingly slow and ways to speed it up. Okay, so I'm just going to start with this example here. Let's say you've got a data frame that has 400,000 rows and 150 columns, and I'm just generating some random data here with RNorm. And this data is I picked it because it's a good size for this demonstration. So there's nothing special about this. It's just a good size and good timing for this for demonstrations here. Okay, so one thing you might do is I'll write a function that will normalize the columns. So let's say I want to take each of these 150 columns and make it so that the mean of that column is 0. And so the mean of the column is 0. So I take the original data for each column, and then I find the mean of that, and then subtract that mean from each column. So I've got this function norm calls, and what it does is it takes the mean of every column by using the apply function like this, and then it subtracts the mean that I've calculated from each column, and then it returns the resulting data frame. So this is just my first pass attempt at normalizing these columns. Okay, so then after I define this function, then I would say norm calls data on the data that I've generated. Okay, so let's try that. Oops. So I've got my code here. This is the same code that you saw before. First, I'll generate the data. This takes a few seconds. Maybe more than a few seconds. But fortunately, we only have to do this part once. Okay, so it's done. Define my function. Oops, sorry, I typed an extra character there accidentally. Sorry about that. So define my function. Oh, I'm sorry. Okay. It is trying to print out the data right now, and that there's a lot of it, so it's very slow. So let me just try to stop this and restart my R session. Okay. All right, so starting over, let's create the data. Okay, and then we'll define our function norm calls, and then we'll run the function, and this time we'll wrap it in invisible so it doesn't try to print it out, because that is very slow. All right, so now if you saw, that took a few seconds to run that. Again, I'll do it again so you can see. It takes a few seconds. It's sitting there, and then returns to the console. Okay, so that's this is it takes a few seconds, and if we want to take a closer look at the amount of time that it takes, sort of the first pass thing that you might do is just run system.time. So you have all the same code and you wrap it in system.time, and this tells you how long it takes to run the code inside of it. All right, so let's try that. I have it right here. And the total time that took was 2.6 seconds. Okay, so if you're trying to figure out what parts of your code are slow or how long things are taking, this is the first thing that you might do, is just to see how long does it take. But then after that, typically you're left to your own devices, and you have to take a look at your code and think about what sort of take guesses at what parts are slow and what parts are not slow. And that can require, to get an accurate idea of the parts that are expensive, that can take a lot of experience. And sometimes even, your what you think is slow it's not actually slow. So in order to help out and figure out what parts are slow so you can speed them up, you can use profiling tools. So so R has a built-in profiler. It's a sampling profiler, and what it does is it will tell you what the R process is doing over time. So to use it, it's really simple. You just say rprof, then you run your code, and you say rprof null, and that stops the profiler. So what happens is let's say this is time along the x-axis here. The R process does a lot of computation. It does a lot of computation, and then periodically, I believe the default is 20 milliseconds. Every 20 milliseconds, the profiler stops the R process, and it queries it and says, what function are you in right now? And our code is very simple, so it'll be in the normcalls function. And then it records that, it saves that, and then it goes back, and the R process does all sorts of computation here, lots of computations, and then it gets stopped again by the profiler. And again, it's in the normcalls function, so it writes that, it saves that again, and it keeps going. It does this every 20 milliseconds until it's done. So now, obviously, in this case, if this is all that it recorded, this is not particularly helpful information. We know that we're in the normcalls function all the way in this entire time here, but it actually records more information than that. What it does is it records these, not just the sort of the outermost function that's being called, which was normcalls. It will also record other functions in the what's called the call stack. So normcalls, it calls apply, right? So this is our call to normcalls here. This is our function definition, and that it first called apply. And apply, it turns out, we'll call as.matrix, as.matrix.dataframe on list. So this is the call stack, and then these are all R functions, and then at the top of the call stack, typically the functions that are at the top of this will call it to C code, which the profiler does not record and does not give any insight into. So that's what might happen at the first sample, and maybe the second sample. The third sample, there's something different that happens, like normcalls calls apply. So apply then calls mean, which calls mean.default, and so on. And then eventually, after it does all of the apply stuff, then it will call the minus function, because minus, these operators in R are all functions. So this is the information that the sampling profiler will record. Now, the data that comes out of rprof, the built-in R profiler, it's a little bit. It takes some practice and some expertise to work with. So we have a tool. Oops. Oh yes. Actually, I should. Oops. Let's go back to here. One important thing to remember is that if this is like the full complexity of all the stuff that that the computer is doing and all the processing that it's doing, this is what the profiler is going to tell you. It's a very low resolution view of what the computer is doing. But that's okay, because for this sort of thing, we're trying to find the large, expensive things, large, slow, expensive things, and speed them up. So we don't need to look at all the fine detail typically in order to make improvements. We can see the large features here, like the continents and the oceans, and that's sort of like, those are the large things that we need to look at for speeding up our code. Okay, so as I was saying, the data that comes out of the profiler and the built-in tools for R they do take some practice and expertise to use. So I've worked on this package called Profvis, which makes it a lot easier to interact with and interpret the profiling information that gets recorded. So to use it, you say install that package's Profvis, and then library Profvis. And then you just take your code and the same code, and you wrap it in Profvis, similar to how we used system.time before, but this time we just use Profvis. Okay, so I'll show you what happens if we do that. Okay, we've got this. This is our code here. Is there, so let's run it. And I'm running this from within RStudio. And when you're in RStudio, it just pops up in this panel right here. If you're running it outside of RStudio, it'll come up in a web browser, and the interactions will be exactly the same. So, okay, so there's two parts here that show up in the beginning. This is the code here, right? This is all the code that we ran, and then on the bottom there's a flame graph. So the code is pretty self-explanatory. Well, the code itself is self-explanatory. On the right, there's two little graphs for each line of code that are useful. So the first is that, well, the one that's most important is the time. So there's about 1,700 milliseconds spent on this line of code, and about 280 milliseconds spent on this line of code. And as you can see, so in this line of code, there is about 2,000 milliseconds. Now, it actually turns out that this 2010 is the sum of these two lines of code. So it spent time in this line of code, but this line of code all called out to this function, and so it's ended up spending time within these other two lines of code as well. So that's the time column. The memory column shows how much memory was allocated and deallocated within each line of code. So in the call to this norm calls function, there was 2,000 megabytes of memory allocated and 900 megabytes deallocated. I'll talk a little bit more about that in a bit. Okay, so that's the code, and there's this corresponding thing on the bottom called a flame graph. And this is really important. So in the flame graph, on the x-axis is time. So this is at the beginning when we started, and it goes across over time as time was progressing, and this is where it ended. So all the time was spent in the norm calls function. And norm calls called out to apply, which we saw before in that diagram that I showed you. And apply called as.matrix, which called a bunch of other functions, as.matrix at data frame and unlist. After apply finishes doing as.matrix, and it calls aperm. And then it calls this function. What happens to be the function we passed in, which is the mean function. And then after apply finished, then the minus function was called the minus function. And this whole thing took about 2 seconds. So there's this GC thing, which is a garbage collection event. This is when R allocates a lot of memory, and then when it decides it needs to free up some of the memory that it had previously allocated, it does a garbage collection, which stops everything, all the processing, and it just spends time clearing up memory. And that's where the memory deallocations happen. So that minus 903 megabytes, that's the garbage collection event right there. Okay, so now if we talk about this code a little, let's talk about the code a little bit and what's expensive here. So the apply function, first it converts our data frame to a matrix. And then it calls aperm on it, which actually it's essentially transposing the matrix. And so it does all of that work. That takes almost 800 milliseconds, and that's just to transform the data into a form before it can start doing the actual work, which is taking the mean of each column. All right, so that seems kind of a waste. So let's if we think about some other ways of getting the means of columns, that might be helpful. So here's one way that we can do it. We can just find some other ways of doing this and then run Profvis on them. So here's 4 ways of doing it. So the first was to apply the mean function using the apply function. The next is to do column means. There is a built-in function in R for taking column means, and it seems like that should be pretty fast, right? If there's a specialized function for that. And there's 2 other ways that we're going to do here using lapply and vapply. So it turns out that this is using the fact that data frames in R are implemented as lists. So a data frame is actually a list of vectors. Each column is one of those vectors. So we can apply, lapply the mean function over all of those columns just by calling it like this. And a vapply does basically the same thing, except it enforces a return type, which might be useful. But they're essentially the same thing. So if we run this code, let's go back to here. If we run it, then this will give us the ability to compare these 4 different ways of getting the means. So the first is apply. We knew this was slow. This time it's took about 1,700 milliseconds. The next way that we tried was call means, which is also, it's much faster. It's about 4 times faster. But it's not the fastest way to do it, which may be a little bit surprising. And then lapply and vapply are both very fast. So these are both over, each of these is over 10 times faster than our original method of doing it. Now, again, this profiler gives us some useful information. Not just, it tells us not just that, call means is slower, but it also gives us some insight into why. Well, oh yes, and by the way, you can zoom in here with the flame graph if you want a closer look. So the reason that it's slower is because, again, call means, like the apply function, converts the data to a matrix first. And it actually, if you read the documentation for call means, it says that that's what it's for, but it is for matrix data. But if you give it a data frame, it will course it to a matrix, and that turns out to be an expensive operation. And then after that, this little empty block here, this is where it's calling out to C code to actually take the means. And then it's very fast. But lapply and vapply are they don't have that that matrix conversion step, and so they're overall much faster than calling call means or apply. Okay, so then we can go back and have a more optimized version of the code. In this example, I used vapply just because it's a little bit more convenient to work with the data that comes out of it, but could have used lapply here as well. So we just make a copy of the data, take the means of each column, and then we would modify that data frame by subtracting the means. All right, so let's take a quick look at that. Okay, so if this is our original thing, we can see, we worked on the most expensive, the slowest part of the code first, which was this line. And now that part is much faster. This is the corresponding part in our new code. And in this part, now it's this line that's slower. So there's actually some room for improvement here, but this already, this is much, much faster than our original code. Our originally it took, let's see, how long was it? About 2 seconds to do the normalizing, and now it's taking us about 400 milliseconds. So it's about 5 times faster just by doing that one optimization. But again, there's a room for a little bit more improvement here, but I'm not going to go into depth about that. Okay, so all right, I want to show a second example. This is something that actually this is a problem that came up while I was working on Profvis and working on it processing the data. So the data that comes out of that's recorded by the profiler looks like this. It actually gets saved to a text file, and this is each line of text represents one sample, one moment in time, and this is the call stack. So it's actually in the order. So apply is at the bottom of the call stack, and then as matrix data frame, and then unlist. And the next sample is like that. And then a sample further down the line might only have might be calling apply and then a-perm, et cetera, et cetera. And there's about 750 lines of this. And we need this to be transformed into a data frame that looks like this, where each row in the data frame represents one of these samples. And it records the original row that it came in, which is essentially which time step it was at, and then the column, which was well, it's in reversed order here, but this is essentially the depth in the call stack, and then the label. So the way it does this is it takes each line, converts it to a data frame, and then into a small data frame like this, this 4-row data frame. Each line gets turned into a data frame, and then it sticks all those data frames together. That's how it did it originally. And I'm just going to walk through this code real quick, and you can look at some of the things that might seem like they're slow. All right, so first we read in the text file. We create a list to store all this, all those data frames that the little data frames that we create. And then for each line, we process the line of text. So first we save the line in variable, we split up the line on spaces, then we create a data frame from that, and then we store the data frame in the list. And then we just loop over it and keep doing this for each line. And then at the end, we combine all these data frames together by calling do.call and rbind. Okay, so let's just run this code real quick. And let's see. This is okay. So it takes about 400 milliseconds here, and we can see what's expensive. So, well, let's take a look first. Why don't we take a look at some of the things that seem like they might be expensive. So, so these are typical things that everyone in our community, well, not everyone, but people in our community, are rules of thumb that are for things that are slow. So first, this list that I have here, it's not pre-allocated. I'm using a for loop, which is, people tend to say to avoid for loops because they can be slow. And then I'm growing this list in the loop. So because I did not pre-allocate the list, every time I add something to it, it has to allocate a whole new list. And so these are things that seem like they should be expensive. But if we take a look at the actual profiling result here, that's not necessarily the case of how expensive. So again, it took about 400 milliseconds to do all this, and most of the time, as we can see, was spent here creating a data frame. There's some time spent splitting up the string, but much more time spent creating the data frames, and at the end, putting the data frames together with the do call and rbind. So that's interesting. It's actually storing the data and growing this list in the loop. That was actually not very expensive. It looks like that took about 20 milliseconds total. So that's a negligible amount of time compared to all the other stuff that's happening. So yeah, so that just goes to show that sometimes it's counterintuitive what the expensive parts are. Creating data frames, it turns out, is expensive in R. So now I won't go into detail about this, but the way that you can solve this, or that I solved this particular problem, was instead of creating a data frame for each iteration of the loop, is to put the data in a list, because that's essentially what a data frame is. It's essentially a list, but a data frame enforces a few things, like each of the vectors needs to be the same length. But if we're careful, we can just use a list instead, and then I create a data frame at the end by calling data.frame and then extracting out each of these columns from the list of lists that I have. But again, I won't go into detail about this, but I just wanted to show you that now that since we know what the actual expensive parts are here, instead of spending time trying to optimize the wrong thing, like converting it from a for loop to lapply or something like that, we could spend time fixing the things that are actually expensive, which is the data frame creation. And if I run this faster version of the code, the whole thing takes 20 milliseconds, okay, as opposed to 400. And that's we can do this because we know what the actual slow parts of the code are, and that's what the profiling tools give us information about. Okay, so those are my two examples, and as you can see, I've been using Profvis with RStudio, and I believe this still requires a recent daily build of RStudio, which you can find if you just Google for it, RStudio daily build. And RStudio has some other nice integration features, which I want to show you. So First is that there is a profiling menu. So I've been running all of this stuff by wrapping these all my code in Profvis, but you don't have to do it that way if you're using RStudio. Okay, so what you can do is you can say select all of your code that you want to run. This is not wrapped in Profvis. This is like if you're running your your code in your whatever R file you're working on. You can say profile and then profile selected lines. This takes a few seconds, and then it shows up here like that. So you don't have to modify your code and add Profvis in there anywhere. And once you have it like this, and if you want to save it for later, you can just click on the Save button here, and let's just say I'll call this temp. So let's save it as temp.rprofvis. Okay, so if I close that and then I find it, the file here. So it's temp.rprofvis, and if I double-click on it, it'll open it up again here. And also, it turns out that if you want to share this with people, there's a couple ways of doing it. What you can do is this rprofvis file is really just an HTML file. So if I rename it to temp.html and then double-click on it, it opens it up in a web browser, and I can interact with it the same way that I was interacting with it before. Okay. Because it is just a web page. So that's one way of sharing it, is that you can save it as an HTML file and send it to somebody. But you can also there's a publish button here, and if you hit that, you can publish it to RPubs. So, and if you're not familiar with RPubs, it's just a free hosting service that RStudio runs for documents. So I'll just publish it, and I'll say this is a Profvis example, continue, and then it's online at this URL here. So then you can share this URL with people, and you can, if you want to show them how the profiling of your code and what's fast and slow, you can just send them that URL. So that's a nice, convenient way of doing it. Okay, and one other thing I want to show you is that you can also do previously, I selected my code and I ran profile selected lines. Another way that you can do it is you can say profile, start profiling, and then run your code. So, well, I guess I only have to run this one here. So I started profiling, then I ran that line of code, and it's still profiling. But then if I hit stop, it stops, and then it pops up the information here. But when you do it this way, you don't get the source code showing up here. So it's not quite as nice that way. You don't get to explore the code that you are running. Okay. Oh yes, and it's also, as I mentioned before, you can use Profvis without RStudio. If you're using R in the terminal, or R GUI, or say R from Emacs, and you run Profvis, it will open it up in a separate web browser instead of popping it up in that in the RStudio panel like I was working with there. Okay, and all right, so that pretty much wraps things up. So some things to remember. Hopefully, from this, you've learned how the sampling profiler works, and you've got a feel for the Profvis interface, and also we've learned that sometimes the performance bottlenecks are counterintuitive, and it's really useful to have visualizations tools like Profvis in order to help figure out what those bottlenecks are so that you can fix them. Now, if you go to the website for the package, it's rstudio.github.io/Profvis. There's a lot more information there. There's a lot of details that I've glossed over in this talk, and if you're curious about those, curious about learning more about it, you can visit the website there. Okay, and I think I can take some questions now. So first question is, I run code over a cluster. Is there a way to pull the profile result to local? I don't think that the profiler will give appropriate information if you're running code on a cluster or in a distributed system. So I don't think, unfortunately, the the profile records the information that's necessary in order to give you the information that you want there. Let's see. Here's another one. Do you have to define the functions in the Profvis call, or can you just call the function? That's a really good question. So in my examples, I was defining the function inside of the Profvis call, and what that gives you is that when you do it that way, you can view the code in the code viewer. If the function is defined outside of the Profvis call, then you won't be able to see it in the code viewer. So that's what that gives you. Now, there are ways of loading, if you're, say, developing a package and you want to load a package so that you can see all the source in the package, there's ways of doing that which are in the website. But generally speaking, it's best to run all of the functions in Profvis so that you can explore them. Okay. Okay, when I tried Profvis this spring in RStudio on a Linux machine, it did not work. It only worked in Windows RStudio. Any progress? That is surprising to me. So it should work in RStudio and Linux, and if it doesn't, that's a bug. So now it's possible that if you had an old version of RStudio, it might not have come up in RStudio if that was the issue. But Profvis itself should work fine across all our platforms. Okay, how will this work with Shiny? That is a really good question. Why don't I try to find an example here? Okay. Okay, GitHub. Oops. Profvis.github. Oops, sorry, it's RStudio. Profvis. Okay. So I have an example here of a Shiny application, and I can run it interactively too. But on this website, there's an example about profiling a Shiny application. Actually, I'll just run this code since it's right there. Let's see, RStudio. Okay, so I'm just using run example to run one of the built-in Shiny examples. Nope, not very Shiny. Let's do that. Okay, so this is our tab sets example. Move the slide around a few times. Summary. Okay. And then when I close the Shiny app, Profvis will know that it's finished and it'll process the data. It takes a little time to process it. Okay, now here we go. Let me pop this out so it's a little bit larger. Okay, so this is the Shiny app. So the whole thing was within this run example, which then called run app, and the important things to look at are these outputs here. So this is blue, or well, I guess it might be hard to tell. It's actually a light blue output $plot here, and you notice I moved that slider a bunch of times, and so every time it calls output $, every time I move that slider, it would re-render this plot, and so this gives you a view of like what's taking time. And I happen to have installed Shiny in the way that it displays all the source code for Shiny here, so you can actually look at it's showing me all the internals for Shiny when I mouse over it, that's actually the reason that this is a little bit the interactions are a little bit slow here. So output $plot calls a bunch of stuff, and then it ended up calling hist, which was in the example, and it called plot, and so on and so on. Zoom in and get a little bit better look at this. But this gives you an idea of like what takes time in the Shiny application. Now this is you'll probably notice that the call stack is significantly deeper than in those simple examples that I showed earlier. But it's actually far more complicated than that. There's this hide internal function calls checkbox here. And let me split it the other way. Okay, so I have it split vertically instead of horizontally. So this is actually the full complexity of what's happening in Shiny, and you can see there's just, you know, there's a lot of function calls, so normally we try to hide all that unnecessary information by using hide function calls, and so you see something like this. It's a little bit easier to interpret. And again, now this is also in the if you go to the website for Profvis, it has the same example, and on the website there's all these things are interactive as well. So because they are, Profvis just generates web pages, so they can be embedded into our Markdown documents, which is how this is all generated. So I hope that's helpful. I hope that gives some understanding of using it with Shiny. Okay, let's see. So here's a question. I don't see the profile item in the top command list. It says I'm running the current version of RStudio. Do I need to use the daily update? So the daily update of RStudio. So I'm using, let's see, RStudio, where is it? About RStudio. This is version 0.99.1281. These daily updates, there's like sort of the release version of RStudio, and then there's these daily builds. The release versions will say they're up to date, but if you want all the cutting edge features, then you want to use the daily builds. So we can just, say RStudio daily, and then it'll come up here, RStudio daily builds. I'm on a Mac, so I'd say desktop Mac, and then they're just right here. So I would just download and install this. Okay, here's a question. We discussed why 2,000 megabytes is allocated, but only 903 was deallocated. Did the resulting new data frame need 1 gigabyte of storage? And that was back with the, I believe it was this example here. So what happened was it allocated a lot of memory while it was taking these means. It didn't deallocate it all because, as you can see during this processing, there was a garbage collection event that happened partway through, but at the end there wasn't another garbage collection event. If there was another garbage collection event here, then I believe the total memory used would have deallocated the same amount that it had allocated. Well, not exactly, because it still needed to allocate some memory for the means, but that's relatively small. So, and there's ways of triggering the garbage collection. There's a function called GC, which will just trigger garbage collection. So if I had done that at the end, it would probably come out that way. Okay. All right, so here's another question. Why is matrix sizing a data frame so computationally expensive? It's actually not computationally expensive. It just takes a lot of memory. It requires a lot of memory allocation and moving stuff around in memory. That's the expensive part. And in fact, a lot of times in R, when you have things that take a lot of time, but they're surprisingly, they're things that are slow in R but are surprisingly slow. It's often because they're moving a lot of memory around in a way that's inefficient. So some of the stuff that I did here, using instead of converting to a matrix and then transposing it with aperm, which is what apply does, and just using lapply directly, that saved time because it didn't have to move stuff around in memory a lot. Okay. Another question here. Can I save the profile file within RCode? So instead of using the RStudio interface, and it is possible. So if you want to be able to share this with people without, outside of RStudio or doing a programmatic way, you can do it. So let's see. There's a frequently asked questions section of Profvis, and it is. How do I share? There it is. Oh, at the top. Okay, so you just run Profvis, save that in a variable P, and then you say HTML widgets : save widget, and then set the file name. That's how you'd save it without using the RStudio graphical interface. Okay, so this is a really good one. In the flame graph, do the blank spaces correspond to C code, C or C++ code being executed, or time that you aren't clicking on anything in the Shiny site? So let's see. So where is that last one that we did? Okay, so in this example, so the blank spaces. So well, if it's these blank spaces, this means that there's, or at the very top above everything else, that's time that is spent probably in C code. There's spaces between these, this sort of empty space between things. This is just because in these areas the call stack is not as deep. There weren't as many function calls, so that's why there's nothing in between them. Now there are these cells that are white. There are cells in the flame graph that are yellow, and there's ones that are white. The yellow ones are ones for which we have source refs, and that means that we can show you the source code in the code panel on the left. So that was the code for this Shiny application, and for Shiny itself, because as I mentioned, I had loaded Shiny with all the source refs, and so that I can view them all. I can view all the Shiny code in that code panel. The white stuff, this is calling code that we don't have source refs for. So these are for packages that we don't have what's called source refs installed, and these are probably in the base or these functions are probably in the base package, and those are not installed with source refs by default in R. So we just don't have them. There's ways to do it, so you can install these packages with source refs, but I haven't done that. Okay. Okay. How do you install Shiny to show internal functions? Great. Okay, we were just talking about this. So again, this is in the frequently asked questions sections of the website. Let's see. How do we get code from an R package to show in the code panel? So there's this question here, and you need to install the package with source refs. So we typically, you'd say install packages and the package name, type equals source, and then you pass it this install option with keep source. And so any package that you install that way, the internals of that package will show in the code panel of Profvis. Does coding simpler but nested functions worsen memory usage? I mean, is it a good practice to define a function inside of another function that will call it? Defining functions within other functions in R has a very, very low memory overhead and also memory and time overhead. So that's actually, it's pretty much, there's very little cost to doing that, and if you define functions within functions, and it can often help, like, just to mentally sort out your code. So if you have a place where you're thinking about doing that, it's probably a good idea. But there's probably no real performance benefit or penalty for doing that. Okay, here's another one. Will Profvis work with code being run in parallel, say with a parallel package? And I believe the answer is no. I haven't really tried this out myself. I think somebody told me that it did not work. And that's because the built-in R profiler doesn't record information for with parallel that can be useful. It doesn't record the information that you need when you're profiling using parallel.